Hi everyone, welcome to our Trig 1 unit for Pre-Calculus 12. Today we're going to be looking at the beginning of trigonometry and seeing what we can do as an extension from Pre-Calculus 11. So here's a little review. Last year we studied almost all in degrees, and depending on what teacher you had, you may have taken a little bit of a look at radians. So one of the common questions we always get is, why are there 360 degrees around a circle? 360 seems like an arbitrary number. So there's a couple reasons. Number one is 360 is nicely divisible. There's 24 different factors that go into 360. And if you look at the numbers 1 through 10, with the exception of number 7, they're all divisible by 360. So when you start drawing a circle and you want to divide it into certain parts, it's very easily divisible. Another reason that I've heard is that there's 365 days to go around the sun, and so if it takes 365 days, that was a number that was very close to 360. And finally, the Babylonians, they used to count using base 60, and so if you think of how many seconds there are or how many minutes there are, there's 60 seconds, 60 minutes. It's related to that number 360. Okay, so regardless, we have 360 degrees around a circle, and if you want to be able to review some terminology, we can say we have quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So we begin with our initial arm, always right here on the x-axis, right at the beginning of quadrant 1, and when we move in a counterclockwise rotation, you're going to create some sort of angle around a standard position circle. So wherever you finish, we will call this right here, we'll call that our terminal arm. Okay. If you wanted to create a negative angle, then instead of going up, you would just go down. And so all the way around a circle here, we have something that is 365 degrees. So quickly, just as a review right now, if we wanted to be able to do a sketch, nothing needs to be exact here, and we want to be able to graph 110 degrees, we could easily sketch that by saying somewhere right around there, that would be 110. So just as a review, this right here stands for theta. So if you have negative 150 degrees, we now know instead of going forwards, we're going to go backwards. So negative 150 will end up somewhere right around here. 400 degrees, we would do one full rotation. There's 360, and then up here would be around 400. And then negative 500 degrees, we have negative 360, negative 450, negative 500 would be somewhere in quadrant 3. So if you wanted to review your quadrants, we have quadrant 2, quadrant 3, quadrant 1, and quadrant 4. Okay. Hey, what do you call a number that walks around everywhere? A roaming numeral. All right, okay, not my best. Here we go. All right, let's take a look at the unit circle. So the unit circle is defined as, when you go around a circle, it's defined as having a radius of 1 unit. And specifically here, we have point P traveling around the unit circle, and its coordinate would end at an x, y point right there. And we're going to use unit circles a whole bunch over the next couple of units. So bounded by this unit circle, if it says sketch 230 degrees and 590 degrees on the same unit circle, we could do that here. We have 230 degrees somewhere around right there. And if we were to draw 590 degrees, well, what would happen? We would go around our full 360. And then when you come back here, you would be in the exact same spot. So if I was to sketch this right here, you actually couldn't tell the difference between the two angles. So when you have an angle that ends in the exact same spot and they share the same terminal arm, then we're going to say coterminal angles have the same terminal arm. Okay, now a big difference between pre-calculus 11 and pre-calculus 12 is that while we may have been introduced to radians in pre-calculus 11, we're going to spend the majority of our time talking about radians in pre-calculus 12. Now, radians is one form of measurement, degrees is one form of measurement, but there's so many arbitrary forms of measurement that you could possibly come up with. So just to show an example right here, if you have something where you're saying, hey, this is 360 degrees to go fully around a circle, we could create our own type of measurement. So right here, I'll draw another circle, and we'll call these wongs. And we're going to say to go all the way around a circle is going to take, we're going to say it's going to take 10 wongs. All right. So if we wanted to have some sort of comparison, we could say 360 degrees is equal to 10 wongs. So could you come up with an answer then if it said, well, if 360 degrees is equal to 10 wongs, then 150 degrees would be equal to blank wongs. So if you wanted to be able to create something for this, you could set up a ratio and you could compare them. So we could say something like this. We know that 10 wongs was equal to 360 degrees. And we're going to say if we have 150 degrees, that would be equivalent to a certain number of wongs. So we could cross multiply right here and we can see what happens from that. So when we do that, we would get 150 times 10 is going to equal 360 wongs. Divide by 360, divide by 360, and you are going to get something like 4.16 repeated wongs. You could say 25 over 6. Wongs likes to go in decimals, so we'll say 4.16 wongs. Okay, so if all of that was a little bit strange, let's take a look at radians. So we use radians because it's a natural form of measurement. Simply put, it's going to tell us the amount we go around a circle. So probably the best way to take a look at this is to say that circumference is equal to 2 pi r. So if you think about something like that, in a unit circle, if your radius is equal to 1, and right here we have a radius of 1. By definition, 1 radian would be taking its radius, pretend it was on a string, and you could wrap it around the circle. So right there, here, that would be 1 radian. Well, if you were to do that and you were to continually wrap that around, how many radians would you have going around a circle? Well, looking at our unit circle example right here, we know that circumference, the amount it takes to go around a circle, is 2 pi r. And if our radius is 1, it is going to take 2 pi units to go all the way around a circle. So the distance in radians around a circle for 1 rotation is 2 pi. Here's an illustration that shows this a little bit better. Here we have 1 radian, 2, 3, 4, 5, 6, and then there's a little bit more. So if you were to approximate, you could say that's like 6.28, which is 2 pi. So what we're saying is 360 degrees is going to be equal to 2 pi radians. Now, when we write radians, we don't have a special symbol to give with it. We don't write a little circle up top like we had for our degrees or for our wongs. So we're just going to say 2 pi. And if there is no notation there, we know that we're measuring it in radians. So instead of saying 360 degrees is equivalent to 2 pi radians, what we could do is we could just simplify it and we could say that means that 180 degrees will be equal to 1 pi. Okay, so our task right now is, are we going to be able to convert from degrees to radians and vice versa? So we just did a little bit of this. We said 360 degrees is equal to 2 pi radians, which means 180 degrees was equal to pi radians. And you'll notice that we have our special angle triangle ratios right here. And just like we said with 360 at the start, these are some nicely divisible numbers. So if you think about this, 90 degrees, well, 90 degrees I know is a quarter of 360. So you could compare it to 360, but I think comparing it to this 180 and this pi is going to be a little bit easier. So if we half 180, we get 90. And if we half pi, we get pi over 2. And if you keep comparing it to the 180, you could say, well, I know that 60 goes into 180 3 times. So this is going to be pi over 3. And 45 is going to be pi over 4. 30 is going to be pi over 6, which means 1 degree would be pi over 180. Okay, so what we could do is let's look at this first right here, and let's see if we can come up with a way of being able to convert where we can do some of these in our head without having to rely on some sort of formula. If you want to take a look at going from radians to degrees, I think that these three are going to be easier. These ratios right here, you're going to see over and over again over the next couple months, so they will become second nature. If you take one of the 3 examples that we just looked at right now, and you want to convert 7 pi over 6 radians into degrees, I think the easiest way to take a look at it would be to say, well, if I look back at this top chart and I see pi over 6, and I know that pi over 6 is equal to 30 degrees. So 7 pi over 6 would mean that I have 7 chunks of 30 degrees. So 7 chunks of 30 degrees would give me 210 degrees. If I have pi over 3 right here, pi over 3 is 60 degrees, and if I have 5 of those, I would have 300 degrees. And pi over 4, that's 45 degrees. If I have 3 of those, I would have 135 degrees. So you can see that when you have these nice ratios where you have a denominator of 3 or 4 or 6, you're going to be able to solve for those pretty quickly going from radians to degrees. If you want to go from degrees to radians, you could try to break them up into chunks. So for example, you could say something like, well, 120 degrees is 2 chunks of 60. And I know that 60 is pi over 3, so I could say this would be 2 pi over 3s. 150 would be 5 groups of 30. So you could say 30 degrees was pi over 6, so I have 5 pi over 6, and so on and so on. So here's 5 groups of 45, and here's 4 groups of 60. And so then you could say that would be 4 pi over 3, and this would be 5 pi over 4. Now that might seem a little bit quick, and if it's something where you're not comfortable with those numbers, then we can always resort back to saying, well, how could you go with anything from degrees into radians? Well, let's take this first example here. If you had 120 degrees and you wanted to convert it to radians, you can always times it by pi over 180. So this is just taking the same way that we did the ratio to convert from wongs to degrees. We can create some sort of a ratio, and the ratio from degrees to radians will always be to multiply it by pi over 180. So if you can do that, you can reduce that to 2/3, and you would get 2 pi over 3. If you have something in radians and you want to go to degrees, it's just going to be the reciprocal. So if you have something here where you could say, well, I have 3 pi over 4 radians and I want to convert this to degrees, well, now we're just going to times it by 180 over pi. You know that if you want to convert it to degrees 100% of the time, your pi's will reduce with each other there, and then you could try and reduce this as much as you want from that, but 3 pi over 4 would give us 135 degrees. Okay. So here's a couple more examples to be able to practice that. We did 240 before, so I'm not going to do that one again with you right here. But if you have something like 72 degrees, you can times that by, well, degrees to radians. So you can look up right there. You can times it by pi over 180. And if you times it by pi over 180, then you could get something that would be 2 pi over 5. Now it says round to 2 decimal places where necessary. We'll leave it as 2 pi over 5. You could convert that to a decimal, and you could say that that's also 1.26, but sometimes leaving it in the exact form is nice. 8 pi over 3. Well, I'm going to try and use the method that we did before. Pi over 3 is 60 degrees, and if I have 8 of those, and I'm going to have 480 degrees. 2.13. Now, because there's no degree sign, we know that this is measuring in radians, and there is no pi in it. It's just 2.13 radians. And so we want to be able to see what that would look like if we wanted to convert it into degrees. So we could take that and we could times it by 180 over pi, and if we do that, we're going to get, well, let's go with 122 degrees. Okay, I know that's not to 2 decimal places, but we'll just say 122 is a nice number there. Okay, so determine 3 angles that are coterminal. Coterminal, they share the same terminal arm with the following angles. So if you have 300 degrees, we know that every time you do a full rotation, positive or negative, it's going to create something that's going to be coterminal. So if we add 360, or if we minus multiples of 360, we'll be able to do that. So for instance, here you could say you could get to 660, you could get to 1020. If you subtracted 360, you could have something like that. And if you have something here where you're in radians, well, instead of adding and subtracting 360s, you need to add and subtract a full rotation, and we know that a full rotation in radians is 2 pi. So here we could say, well, what would happen if we added 2 pi, or if you subtracted 2 pi? Now, sometimes adding fractions won't be the easiest if you don't have a common denominator, so we'll say, instead of saying 2 pi, let's write this with a denominator of 6. So if you write this over 6, we could say 12 pi over 6 or 12 pi over 6 subtracting, and that's the equivalent of 2 pi. So if we add multiples, we can now do this really quickly. So 5 pi over 6 plus 12 pi over 6 is going to give us 17 pi over 6. We could have 29 pi over 6. And if we subtracted 12 pi over 6, we could have negative 7 pi over 6. So as you go round and round in a circle, there are an infinite number of coterminal angles. And if there's an infinite number of coterminal angles, then we want to be able to say, well, what would be something that I can make in terms of a general statement? I want something that's going to represent all angles. So for our first answer, we had 300 degrees, but I know that every time I add or subtract a multiple of 360, I'll be getting another coterminal angle. So an efficient way of saying that is we could say plus 360n, and we have to qualify what n represents. So we're going to define this as where n is any integer. So you recognize e as being the element, so n is the element of all integers. This isn't the best way to write it sometimes. In a lot of BC math textbooks, you'll see this representing n is any integer, but we know that sometimes they might use a different notation. So if you choose to do something different, you can, but for our sake and to be consistent, let's just say any I. So that's saying that n is representing any integer, positive or negative or 0. 5 pi over 6. Well, I know that instead of adding 360 degrees, I'm adding 2 pi, but I have to add some n of 2 pi. So the way we write that is we're going to say plus every 2n pi. And if you wrote 2 pi n, that's also correct, but usually we say 2n pi, where any I. Okay, we got a couple examples right here. Arc length. So arc length, you're going to be given the formula. So arc length equals radius times theta, where theta is going to be the angle given in radians. And so what that means is it's going to give you the portion of the circumference of the circle. And A stands for arc length. R is going to be the radius, and theta is going to be the angle in radians. Okay, so a couple examples here. Determine the arc length of a circle with a radius of 5 and a central angle of 60 degrees. Let's draw this out right here. Okay, and so based off of that, we know A equals R times theta, and we're going to say in this case, we know that the radius is going to be 5, and we know that the angle is 60 degrees. Now, when we measure this, we're talking about the natural form of going around a circle, so it needs to be converted to radians, and we know that 60 degrees was pi over 3 radians. So we could say that the arc length will equal 5 times pi over 3. So the arc length will be 5 pi over 3 radians. Okay. Taking a look at the next example right here, we got, it says find the distance traveled from the tip of the second hand of a watch with a radius of 16 millimeters as it goes from 0 to 40 seconds. So the key here is that from 0 to 40 seconds, that's 2/3 of a full rotation around. And in other words, we want to find out what would be 2/3 of a full circle. If you want to still think in degrees, you could see that that's 240 degrees. And if you converted that to radians, that would be 4 pi over 3 radians. And using A equals R times theta, we want to find the arc length of what it covered. We know that our radius is 16. So we'd have 16 times 4 pi over 3, and that would equal 64 pi over 3 millimeters. Okay, final example for the day. What is the degree measure of a central angle theta opposite an arc of 18 centimeters in a circle of radius 6 centimeters. Okay, so let's do a r theta. So now they're giving us the arc length. They're telling us that the arc length is 18 centimeters. So if we're saying this is 18 centimeters and our radius is 6 centimeters, and they want us to find out what the angle is, well, we could do that. So we could say A equals r times theta. 18 is going to equal 6 times theta. And so now if you have something like that, we could divide by 6, and theta is going to equal 3, but it's going to equal 3 radians because we know theta is measured in radians. So if they're saying what's the degree measure, then we know that we're going to have to take 3 radians and we're going to have to convert that into degrees. And so if we have that, we're going to have to times it by 180 over pi. And if we calculate that to the nearest degree, that is going to give us 172 degrees. Okay, that's lesson 6.1. I hope you guys have a great day.